2 minus a is less than half, and therefore, the sequence an is a divergent sequence. In a similar manner, one can prove that the sequence minus 1 raised to n is a divergent sequence. Now, we have a theorem that a convergent sequence has a unique limit. This is a very useful criteria whenever we want to prove whether the sequence exists or limit of a sequence exists or not. We may use this criteria because once the limit exists, then it must be unique. So, if the limit is not unique, then we conclude that the sequence is not convergent. That is how this is a very useful criteria. We will prove this. Let us begin with a sequence an. Let an be a convergent sequence, and suppose limit of this an is a, and the another limit of this an is b. Now, if a is not b, then we have some positive number epsilon given by mod b minus a, and since the limit of this sequence an is a, by the definition of the definition of a limit of a sequence, there is an integer n1 such that mod an minus a less than epsilon by 2 for all n greater than or equals to n1. Again, the limit of the sequence is b, limit of sequence an is b, and therefore, again by the definition there is n2 belongs to n such that mod an minus b less than epsilon by 2 for all n greater than or equals to n2. Now, let us choose this n0 is a maximum of n1 and n2. Then this mod a minus b is less than or equals to, it is mod a minus an0 plus mod an0 minus b, and from the previous results each quantity is less than epsilon by 2. So, this is less than epsilon by 2 plus epsilon by 2, and epsilon by 2 plus epsilon by 2 is epsilon. So, this is nothing but mod a minus b, and this contradicts that mod a minus b is less than mod a minus b, and this contradiction is because of our wrong supposition that a is not equals to b, and therefore, we must have a equals to b. Once we have a equals to b, it is proved that the limit is unique if it exists. Now, another thing will prove that if an is a convergent sequence, then it must be a bounded sequence. So, for that purpose, we will begin with convergent sequence an, and as this is convergent, there exists integer n0 belongs to n such that mod an minus a less than 1 for n greater than n0. Now, we know this inequality that the absolute value of mod x minus mod y is always less than or equals to mod x minus y for all xy real numbers. So, let us replace x by an and y by a. So, we will get this absolute value of mod an minus mod a is less than 1 for n greater than or equals to n0. And by taking a equals to maximum of all this mod a1, mod a2, mod a3, mod a n0 and mod a plus 1, then always mod an would be less than or equals to a for all n, and thus we have a number. So, that mod an is less than or equals to some number k, that number is a here. So, this sequence an is a bounded sequence. Using similar technique, one can prove the following theorem. It is this theorem that the limit of an is a and limit of bn is b, and if if a is any scalar, then limit of an plus bn is a plus b, and limit of an into bn is it is a into b, and if an is non-zero for all n and a is also non-zero, then limit of 1 by n 1 by an as n tends to infinity equals to 1 by a. Now theorem 3, if limit of an is a, then limit of mod an it is mod a. However, the converse of the above theorem is not true. For example, if we have a sequence of minus 1 raised to n, then the absolute value of this is 1 for all n, and that is a constant sequence 1 which is a convergent. But the original sequence, that minus 1 raised to 1, 1 raised to n is a divergent sequence. Now we will see the Cosy sequence. Sequence an is called a Cosy sequence if for every epsilon greater than 0 there exists n0 belongs to n such that mod an minus am less than epsilon for all nm greater than or equals to n0. We will accept without proof the following theorems. One is the Cosy criterion for convergence. A sequence is convergent if and only if it is a Cosy sequence, and theorem 5 that a monotonic bounded sequence is convergent. Now I will request Kamlesh sir to continue this. He is also from the MS University of Baroda, and he is a very good teacher. Now he will continue this lecture. Kamlesh bhai.
Thank you, Kataria sir. Good afternoon, friends. Kataria sir એ આપણને ઇન્ફાઇનાઇટ સિક્વન્સ વિશે ઘણી સારી માહિતી આપી. આપણને મૂળભૂત વ્યાખ્યાઓ અને એના અગત્યના રિઝલ્ટ્સ વિશે પણ આપણને વાકેફ કરાવ્યા. હવે આપણે ઇન્ફાઇનાઇટ સિક્વન્સના જે આ ગુણધર્મો છે એને લઈને આપણે આગળ ઇન્ફાઇનાઇટ સિરીઝના ટોપિકનો અભ્યાસ કરીશું. પણ જ્યારે પણ આપણે આ ઇન્ફાઇનાઇટ સિરીઝની વાત કરીશું તો એના અભ્યાસમાં પાયામાં બેઝિકમાં આપણને સિક્વન્સની જે પ્રોપર્ટીઝ અને એના જે ગુણધર્મો છે એનો ઉપયોગ કરવાનો રહેશે. તો આપણે શરૂઆત કરીએ સૌપ્રથમ પ્રેઝન્ટેશન જોતા ઇન્ફાઇનાઇટ સિરીઝની વ્યાખ્યા શું છે. તો ઇન્ફાઇનાઇટ સિરીઝ એકચ્યુઅલી એ એક ordered pair છે sequencesની. So I read, an infinite series of real numbers is actually an ordered pair. The first element of the ordered pair is a sequence which I have denoted by AK, and the second sequence I have denoted by SN. Here note that I have used K as index for the first sequence and N as index for the another sequence. It is just for notational convenience. There is a relationship between these two sequences, and that is the following, that the Sn is equal to the first n terms of the first sequence of the ordered pair. That is, Sn is equal to a1 plus a2 up to so on an for all natural numbers. Here both these sequences have a specific name. The first sequence AK is called the sequence of terms, and the second sequence Sn is called the sequence of partial sums of the series An ordered pair Sn. But as you see that this notation is a little bit more inconvenient, and so for notational convenience we will denote this series by this notation, that is summation k is equal to 1 से लेकर infinity ak, and we will now onwards denote the series by this notation. Here I have written where the index starts, but if at places we know that what is the index of summation and from where it starts, we will sometimes not write what exactly is the index and where the series starts from. So now let us move to another important definition, and this is just using the definition of convergence of sequence. So we say that the infinite series summation k is equal to 1 select infinity ak is convergent if the associated sequence of partial sums, as we had seen in the definition, is convergent. Okay, so that means if the limit of the partial sum sequence exists, then we say that the series is convergent, and if the sum, that is the limit of this sequence Sn, is S, then we say that the sum of this series is S. As Kataria sir had just now proved that if a sequence is convergent, then it has got a unique limit. So based on that theorem, we say that if you are given an infinite series for which its a sequence of partial sum is convergent, then we will say that the series has the sum S, and that is the notation we adopt. If this is not the case, that is, if the sequence of partial sums is not convergent, then we will say that the series which we are given is a divergent series. So let us straight away move to an example of an infinite series. So to start with, we take a very simple example which is on the slide. K is 1 select infinity 1 upon k into k plus 1. So we have to check whether this series is divergent or not. So we approach definition and we try to apply the definition to this series and try to see what happens to its partial sum sequence. Now as we know that partial sum sequence is actually nothing but sum of the first n terms of the series. So I just try to first of all simplify the kth term of this series, and which is 1 upon k, k plus 1. If you do a regular partial fraction decomposition, which we usually do in calculus, then we will find out that actually this 1 upon k into k plus 1 can be written like this form, that is 1 upon k minus 1 upon k plus 1. And the benefit of this is, so I will try to now calculate what is Sn for any natural number n. So it is, as we know, the sum of the first n terms of the series. So let us see what happens. So as we had calculated earlier, that first term is 1 upon 1 minus 1 upon 1 plus 1. So that is 1 minus 1 by 2. Similarly, next term is 1 by 2 minus 1 by 3. Here you can see the cancellation at play. See, the second and the third in the sum get cancelled and up to so on. This cancellation moves ahead, and finally we are left only with the first term, that is 1, and the last one, that is minus 1 upon n plus 1. So simplifying this, we actually get that Sn has a very nice formula, and that is n upon n plus 1. So we are lucky in this sequence that Sn is a very nice structure. Why? Because I know how to find out the limit of this sequence. I know that I have L'Hospital's rule in calculus, which is saying that if you have infinity upon infinity form, then you can find out the limit by just merely differentiating the numerator as well as denominator. So applying the same technique, I have written the limit equal to 1, but at the back I have calculated the limit of the function x upon x plus 1. I have not stated the theorem here, but I have used the theorem which says that if a sequence can be derived from a function, and if sequence is defined for all natural, if the function is defined for all natural numbers, then the limit of the sequence and the limit of the function are one and the same. So here the limit of the sequence is 1, and hence I have that the partial sum sequence Sn is convergent. I am least bothered about the value, but if I want to find out what is the sum, then I have that the sum is equal to 1, and I have the answer that my series which is given is convergent. Now while studying series, we encounter a very important class of series, namely a geometric series. You must be all knowing about geometric series, but for the sake of simplicity, I give a definition over here. And geometric series is actually a series of the form given here, that is, it is of the form k is 1 selector infinity a r raised to k minus 1, where a and r are some real numbers of your choice. So, here we state without proof the theorem that for the case of geometric series, we have one convenience, that geometric series, we know what happens about its convergence. And the theorem says that if you are given the geometric series which I had just now stated, then it converges and its sum is a upon 1 minus r if modulus of r is strictly less than 1, and the series is divergent if modulus of r is strictly greater than or equal to 1. Here, in proving this result, we actually use a very fundamental limit, and that is limit n tends to infinity r raised to n is equal to 0 if the real number r is having the property that modulus of r is less than 1. And in proving that limit of the sequence, that is limit of n tends to infinity r raised to n is equal to 0, we actually just use the epsilon definition, that is the basic definition that we are given of the sequence. So, let us just try to apply the theorem that I have just now stated, that is theorem number 1. So, let us look at the series that is here, that is k is 1 selector infinity 2 by 3 to the power k. Now, I know that absolute value of 2 by 3 is 2 by 3, and it's naturally we know that it is less than 1. So, here we can apply the above theorem, since it's less than 1 by the above theorem, this series is convergent. So, in same way you can talk about the series 1 upon 2 raised to k and so on, which are all convergent. Now, let us try to come to a very important result in the topic of infinite series. As you have seen here that while deciding whether a series is convergent or not, we have to actually first of all find out what is the structure of the partial sum sequence Sn, and then after doing that much we have to also find its limit. If we know the techniques to find the limit of the partial sum sequence Sn, then only we will be in a situation to say whether the given series